Okay, so this is another new topic on thermodynamics, a fresh beginning for those who want a fresh beginning. And it's also stuff you probably have seen in high school, some of it at least. So the whole next 4 lectures are devoted to the study of heat, temperature, heat transfer, things like that. So we're going to start with the intuitive definition of temperature everybody has. So let's say you have the notion of hot and cold. Even that requires a little more precision. That introduces the notion of what is called thermodynamic equilibrium. Just like mechanical equilibrium, this is a very important concept. So I'll tell you what equilibrium is with a concrete example. If you take a cup of hot water, then you take another cup of cold water. Each cup, if you wait it sufficiently long, is said to be in a state of equilibrium as long as the cups were isolated from the outside world and not allowed to cool down or heat up. We think they maintain a certain temperature. We say it's in a state of thermal equilibrium because this temperature does not seem to change. Now, we've not defined what temperature is precisely, but we can talk about whether whatever it is has changed or not changed. So it will settle down to some temperature. It will maintain the temperature. Be very careful. If you leave a cup of coffee in this room, it will cool down because the room has got a different temperature. But I'm talking about a cup of coffee that's been isolated from everything. It maintains the temperature. Here's another cup of a cold drink at what we feel is a lower temperature. They are both in a state of equilibrium. Equilibrium is when the macroscopic properties of the system have stopped changing. If you now pour one of these cups into the other one, that's going to be a period when the system is not in equilibrium, in the sense that it doesn't have a well-defined temperature. For example, if you just poured it from the top, the hot stuff is on the top, the cold stuff is on the bottom. That's a period of transition when you really cannot even say what the temperature of the mixture is. Some part. But if you wait long enough till the two parts have gotten to know each other, they will turn into some undrinkable mess. But nice thing is it'll have a well-defined temperature. That's again a system in equilibrium. So you've got to understand that temperature and thermal equilibrium represent gross macroscopic properties, and they're not always defined. At the microscopic level, it's no secret, we all know everything is made of atoms and molecules. The atoms and molecules that form the liquid or the gas always have well-defined states. Each molecule has a certain location, certain velocity. But at a macroscopic level, when you don't look into the fine details, focus on a few things like temperature, they don't always have a well-defined value. That's what you got to understand. Things have a well-defined value when they have settled down. How long does it take to settle down? That's a matter of what system you're studying. Here's another example. Suppose you take a gas and you put it inside this piston here. There's some gas inside. You put some weights, and everything is in equilibrium. We say this in equilibrium because the macroscopic things you can see with your naked eye, nothing is changing. It's going to just sit there. But if you suddenly now remove, say, a third of the weights, the piston is going to rise up, shake around a little bit, maybe settle down in a new location. In between, you will see the piston moving, the gas is turbulent, the pressure is high in some region, low in some regions, then it settles down. This is the notion of systems in equilibrium. Now, whenever a system is in such equilibrium, we can assign to it a temperature that we call T. One of the laws of thermodynamics, called the 0th law, is 0th law because they wrote down the first law, then they went back and had an idea which is even more profound, and they said we'll call it 0th law. 0th law says if A and B are at the same temperature, and B and C are at the same temperature, then A and C are at the same temperature. That seems pretty obvious to you, but that is the whole notion of temperature is predicated on the fact that you can define an attribute called temperature that can be globally compared between two systems that never met directly but met a third system. Let us decide now to be more quantitative. So what we try to do is to find some way to be more precise about how hot and how cold. Let's look at some things in the world that seem to depend on temperature. One thing that seems to depend on temperature is the following. You take this meter stick or make a duplicate of it, you pull it outside and leave it in the room. What you may find is if the room was hotter than the glass case, this rod then expands to a new length. So one way to define temperature is to simply ask, how long is this rod? And somehow correlate the length of the rod with temperature by some fashion. What you need to do first is to define, put some markings on it so that for each extra something it grows, we can say the temperature has gone up by some amount. So we can use markings on this rod compared to the unexpanded length as a measure of temperature. So one way to measure temperature may be take some liquid, put it there, and then put it on hot rooms, and maybe watch the liquid expand to that new height. And then draw some markings, and each marking can be a certain temperature. They had the following idea of a thermometer where you have a lot of fluid in a reservoir, a very thin tube evacuated at the top, and the fluid then is here. So what's clever about this is that if this expands by 1%, your eyes should be good enough to see 1% increase in height. If this fluid expands by 1% in volume, that 1% in volume, when it climbs up this narrow tube, can climb to quite a bit, because the extra volume you get by expansion will be the area of this tube times the extra delta x by which it expands. So you're magnifying the expansion by making all the expanded fluid climb up this extremely narrow tube. In fact, the tube is so narrow, you cannot probably even see it well, which is why they have a little prism that magnifies the mercury or alcohol in a thermometer. We can draw some lines, arbitrary lines, doesn't matter. That can be 0, that can be 5, that can be 19. But you want a better scale than that. Even though that's mathematically adequate, in practice, what people decide is to do it as follows. They said, we want to set up thermometers so that people all over the world, in different parts of the world, different countries, different labs can all agree. So we will make it possible for everyone to make their own thermometer by the following recipe. We will dip this guy in a bucket which has got some ice and some water. That's called the melting point of water. And we dip the thermometer there, and whatever reading we get, we will postulate to be 0 degrees centigrade. Then they said, let's find another universally accessible thing, which, as you all know, is the boiling point of water. That temperature is going to be called 100 degrees. Then you take this column between 0 and 100, and you divide it into 100 equal parts. And that is postulated to be the temperature anywhere between 0 and 100. So that's how the degrees are introduced, and that's the centigrade scale. This is how you have thermometers. There are some problems with this. One problem is that the boiling point of water does not seem to be very reliable, because if you boil water in Aspen, for example, you know it doesn't seem to boil. It seems to boil more readily than in the plains. So who's going to decide what the real temperature is? Now the trouble started when people realized that if you make a thermometer with your favorite fluid, maybe mercury, and I make one with alcohol, they will agree at 0 and they will agree at 100, because that's how you fixed it. You rigged it so at 0, everyone says 0, 100, everyone says 100. But how about 74 degrees or 75 degrees? I say it's 75 if my fluid has climbed 3/4 of the way to the top. At that point, yours may not have climbed 3/4 of the way. In other words, you got two things, two graphs, which at 0 and 100 agree. One graph may be like this, one may be like that. So that when I think it is 75, you may think it's 72. At 100, we will agree because we have cooked it up that way. In other words, it's not true that all liquids expand at the same rate. Finally, they found out a much better solution than these liquids. They found out that if you use a gas, you can define temperature using gases, which have some very, very nice properties. You take some gas in a container, a typical container for me in all whenever I draw anything thermodynamics, it's going to be gas inside some cylinder with some weights on it, and that defines the pressure of the gas. Of course, the pressure will be the mg of these weights divided by the area of the cylinder. That's the pressure, plus atmospheric pressure. And the volume is this, whatever the volume is, base times height. Here is what we ask you to do. Take the product of pressure times volume for any sample of gas. Take some gas, put it in this tank, and now put it on different surfaces, like a hot plate, like a stove, like a tub of water, and measure the temperature using some standard method up to that point, like a mercury thermometer. What you notice is that the temperature measured by some reasonable scheme shows that the product of P times V lies on a straight line. Now, here is the beauty of the gas thermometer. If you take a different gas and you put different amount of a different gas in a different cylinder, you will get some other graph. May look like this. Most important thing is that's also a straight line. If that's also a straight line, it has the following implication you guys can prove at your own leisure, which is that if I think that my gas has climbed 56% of the way of this height to the top, so the temperature is 56 degrees, I ask, what's your gas done? You'll find it's also climbed 56% of the way. It's a property of straight lines. You can show that if you took two straight lines, whatever be their slope, if they agree, if this is 0, this is 100, it's got a different slope. When you have climbed to the halfway point, draw a line at 50 degrees and ask, what has any gas done? They would all have climbed to the halfway point, from the 0 point to the 100 point. In other words, gas thermometers will not only agree at the end points, where they must by construction, they seem to agree all the way in between. All gases have the property that if you calibrate them at 0 and 100, they agree in between. Take the product P times V of your gas by putting it on different surfaces, measure the product, plot this graph. Whenever you're on ice, you call that 0. Whenever you're on boiling water, you call it 100. You find they join, they're connected by a straight line. Then every point in between, if divided equally, leads to equal increase in the product P times V. So P times V for a gas is better than the volume of mercury or volume of water because it doesn't depend on the gas. So everybody can use the gas thermometer. That's why we prefer the gas thermometer. If you cool it below 0 and you ask which way is it going, I don't know. These thermometers indicate somehow the product PV vanishes at a temperature which is minus 273.16, suggesting that there is something very special about that temperature. Because if you took another gas, well, I'm going to do a little cheating here, that also extrapolates to that same temperature. So all gases, all gas thermometers say there is something very special about this temperature because that's when our pressures all vanish. And this is called the absolute 0 of temperature. It's called absolute 0 for many reasons. One is that unlike the 0 of the centigrade, which is by no means the absolute lowest possible temperature, the absolute 0 is the lowest possible temperature. Why? Because the gas pressure can be reduced and reduced and reduced, but the worst that can happen is it can go to 0. That's it. You cannot go below having no pressure. So people decided, you know what, calling this the 0 is kind of artificial. That's based on human obsession with water. But if you think the laws of science describe the whole universe, what about planets where there's no water? So 0 of temperature is going to be set from here. Once they did that, they called that the 0. They needed one other temperature. And they decided that, so if you're starting the new temperature scale, you will put the 0 not at the centigrade, but this is now called Kelvin. And everything will follow a straight line, but to define what 1 degree means, you got to define one other temperature. That's how we define the straight line. that temperature will be called 3.16. But this point is called the triple point of water. What's the triple point of water? You know water and ice can coexist. And you know that water and steam can coexist at 100 degrees. But by varying the pressure and temperature and volume, you can actually find a certain magical point in which both ice, water, and steam can coexist simultaneously. Now that is a unique situation. You cannot get to that by any other means. And that temperature we will call plus 273.16 in these absolute units. So if you found that confusing, I'm just saying the boiling point of water is not a fixed number. You go to the mountains, it changes. But only under one condition can water and ice and steam coexist. You cannot get that any other way. So everybody will agree on that particular situation, and that will be called 273.16 Kelvin. As far as we are concerned, the Kelvin scale is like the centigrade scale, except the 0 has shifted to here. That's the absolute temperature. Whenever I write T from now on, I'm talking about Kelvin.